Today we'll be doing some calculation with the moles. For example, one question is given to you in this way. Okay, molecular mass of water is, you can say molecular mass or molar mass. Let us see molar mass, the better word. Molar mass of water is 18 gram per mole and its density is 1000 kg per meter cube. Now we have to find different things. For example, if he says how many moles are there in 72 gram of water. Now, first thing is we can do this directly by the ratio method. The ratio method tells us, okay, suppose we can take 18 gram is 1 mole, 18 mole, so 18 gram 1 mole, 72 gram x mole, cross multiply, so x will become 72 into 1 divided by 18 and it comes out to be 4.0 mole. This is one answer. When you write mole, it's spelling the MOL, not MOL, it's a symbol of unit MOL. Then we have to see, okay, we can use this equation also. Number of moles is any given mass divided by molar mass. So n given mass is 72 gram. I will change into kg. 72 into 10 power minus 3 becomes kg. Molar mass is also in grams. I will change into kilogram. This one, this gram, and this comes out to be 4.0 moles. So the same answer comes, but I will prefer to use the equations. For example, the mass was given. Now, suppose, so we can use the ratio method by this formula. Suppose if the molecules are given, then how can we do, for example, the second part of this question? Suppose it says, okay, how many moles are in 72 grams of water? Instead of this, he says, how many moles are there in, suppose, 3.01 into 10 power 23 molecules of water. So, how can we find this one? Ratio method, simple. First I can say 6.02 into 10 power 23 molecules say 1 mole. So 3.01 10 power 23 will have x mole. So x will be equal to 1 into 3.01 into 10 power 23 divided by 6.02 into 10 power 23. This this divided by 0.50. This is in 3 significant figure, this is in 2, so I think 3 significant figure answer must be 0.500 mole. Or we can use the equation. The equation is n is equal to number of molecules divided by Avogadro's number. So n, number of molecules 3.01 into 10 power 23, Avogadro's number 6.01 into 10 power 23, and the same answer you get 0.500 mole. Now, sometimes the mass is given and directly they call how many molecules will be there. For example, the question can be in this way: how many molecules will be, how many molecules of water, how many molecules of water will be in, suppose I am saying 5.00 gram of water. Again, the answer must be in 3 significant figures. So let us see. I had 3 methods. First, always the ratio method. Ratio method, I can say 18 gram will have 6.02 into 10 power 23 molecules. So 5 gram will have x. So x will be coming as 5 into 6.02 into 10 power 23 divided by 18. So x will be coming as, I can just calculate this thing. It is 5 into 6.02 exponential 23 divided by 18. It comes out to be 1.67 into 10 power 23 molecules directly. Another method is, I can first find number of, now I will use the equations. And one method is, I can first find the number of moles and by given mass divided by capital molar mass. It is 5 into 10 power minus 3 divided by 18 into 10 power minus 3, and the answer comes out to be 0.278 moles. Now I can find N is equal to N upon Na. So similarly, N will be equal to NNA. Small n number of moles 0.278 multiplied by Avogadro's number 6.02 into 10 power 23, and you get the same answer, 1.67 into 10 power 23 molecules. Of course, you can use this equation directly. I told you in the lectures, okay, M upon M is equal to just N upon Na. So you need this N. So N will be equal to M upon M into Na. Put the values and find the same answer. This is another method. So in that way, we can find the number of molecules in the given mass. Now this moles concept can also be used for finding the diameter of a single molecule and also for the spacing between two molecules. Let us see, for example, they say third part is fourth one, I think. He says find the diameter of single molecule of water and hence state the spacing between two adjacent molecules of water and also state assumptions you have made. Let us first find the diameter of the molecule, and of course diameter is still the same thing. Diameter is always cube root of volume of single molecule V. V is the molecule of single molecule. I can just find first the mass of a single molecule. M is found to be N, capital M upon Na. Mass of single molecule is molar mass divided by Avogadro's number. Molar mass is 18 into 10 power minus 3 kg per mole, and Avogadro's number 6.02 into 10 power 23. And if this is to be done, it comes out to be 2.99 into 10 power minus 26 kg. Now this is the mass of a single molecule. Now I will be calculating the volume of single molecule. Now the concept is same. If there is one molecule or 1000 molecules or how many molecules, its density is always same. So I will find density. I will say density is equal to mass upon volume. Volume will be mass upon density. So mass is 2.99 into 10 power minus 26 divided by 1000, and it becomes 2.99 into 10 power minus 29 meter cube. Now this is the volume of single molecule. Now so diameter will be cube root of this one, 2.99 into 10 power minus 29, and when this cube root is being calculated, this comes out to be 3.1 into 10 power minus 10 meters. I can write in nanometers. Suppose I will write 0.31 into 10 power minus 9 meters. So it is 0.31 nanometer. Now this is the diameter. So he says, what is the spacing between two consecutive molecules? I will say spacing is also same. Spacing between two adjacent molecules is also same, and that is 0.31 nanometers. Now he says what assumptions you have made. Let us see, when we say the diameter is spacing same, how many assumptions we are making. Actually, the first assumption is we say the molecules touch each other but do not overlap. So if this is one radius, this is another radius of the molecule, then this becomes the diameter D, and you will see the spacing also same, the distance between center to center. So first assumption is First assumption is, number one, the molecules touch each other but do not overlap. Number one. Number two assumption is, since we just find the volume as cube root of, diameter as a cube root of volume, it means we are just treating it as a cube. As we say, although molecules are spheres, they are spheres, but we are taking them as cubes. So there are two assumptions. First, molecules touch each other but do not overlap, and second is although molecules are spheres but we are taking them as cubes, simply because if the molecules are very small, so suppose if this is a small molecule, there will be thousands of molecules. You cannot decide whether it's a sphere or the cube. Similarly, if the molecules are very tiny particles, so you cannot say whether they are spheres or they are cubes. You can treat them for estimation purpose. The results will have no effect. There will be no variation in the results for the estimation purpose. So although they are spheres, but we will be taking them as the cubes.